Okay, let's go ahead and get started. So last time we were talking about equations, particularly linear equations, and how to tell the difference between a linear equation and a nonlinear equation. Now, one interesting thing about linear equations is that if we look at their graph, a linear equation will be this straight line, okay? So it will eventually cross through all x values and all y values. Okay, so if we were to continue down here, it keeps going. It might take a while, but eventually it's going to get to something like negative 70 on our y-axis. It's going to eventually get there. Same thing for our x. Maybe we have positive 70 here. If we keep this line going, it's eventually going to get there. Again, it might take a while, but it'll get there. So it can include all values for both x and y. As we saw with one of our examples on Monday, this isn't always the case for nonlinear equations. The example that we saw looks something like this. Okay, and I've drawn it very poorly here, sorry. In fact, let me try that again, just so I can prove my point a little bit easier. Okay, so sometimes we have this line here that, well, they don't cross. So maybe this is something like y equals 2. If we look at this graph, it's never quite going to get to that point. So it's excluding a value. Okay? And this is something important to keep in mind as we go through lecture today. So keep that in mind. Linear equations, they're going to include all of the values for x and y. It doesn't matter. We can plug anything we want in for x and it'll give us out a y. Some nonlinear equations are not going to do that for us. Okay? So, what I want to introduce to us today is the concept of not an equation, but a function. So we're used to seeing things like y equals 2x minus 7. This is a perfectly valid linear equation. Okay? Now, it only takes one thing to change this from an equation to a function, and that is to make y f of x. Okay, f of x, this f with the parentheses and x inside of those parentheses, that's basically just a name. It's a name for our function. But in the name, it tells us a little bit about the function. So f tells us that this is the f function, and then the x tells us what we're plugging in. Okay, so this is the thing that is varying in our equation, which makes sense. For this function, we'd be plugging things in for x, right? And then we'd see what we get out for y. For instance, if I plug in a, let's say negative 2 for x, and that would mean that I have 2 times negative 2 minus 7. So we can go ahead and use our order of operations to figure this one out. 2 times negative 2 is negative 4. And then negative 4 minus another 7, what does that come out to be? Negative what? Nobody? Negative 11. So we can say that f of negative 2 is negative 11. And this is how we work with functions. Again, this thing right here is what we're plugging in. So if we want to plug in a -2, we change that to -2 and plug in a -2 there. And then it gives us this out. F of -2 is -11, which what this says is that if we plug in a -2 for x, our y will be 11. You can think of functions as being little machines. Okay? So with a machine, you put something in. Maybe you put electricity into it, and it turns it into mechanical energy. Okay? You put gasoline in your car, and the output is that it is now able to move. So again, these are like little machines. You put something in, and you get something out. That's all really what functions do. Okay? Now, thinking about these equations like functions allows us to do something else. And that is to put these machines together to make a bigger, more complex machine. Like, think about a car. A car isn't really just one machine. It's a lot of machines working together for a particular output. So in a car you have an engine and a transmission and different motors and things like that. And each one of them is its own little machine. It has an input and an output. But together they make the car, which has its own input and output. Okay, so again, we can take these functions and do the same thing with them. We can put them together to make new things. Let me show you what I mean. Let's say we have two functions. One is f of x equals, I don't know, 5x minus 2. And then another one, let's call g of x equals just 2x. Okay, so these are two separate machines. They have their own little pieces and parts to them, the way that they process their inputs. However, we can put them together and make one machine out of them. And that is with what we call a composition of functions. So if we want to put them together, here's how we do it. Again, this is what we input, right? Well, if we just take this and use it as the input, kind of like gears locking together, we can make these all into one thing. So f of x is going to be g of x, which is 2x. Does that make sense? So now we have one full machine. And let's go ahead and plug things in. Actually, this is not a great way of writing the name for this new thing. A better way would be to say f of g of x. So again, you could write it this way. It's just not a great way of writing it. A lot of people don't write it that way. This is the more accepted way to write the name of this new function. But it's still the same thing. It's still 5 times 2x minus 2. Whoops, wrong way. So let's plug something in. Let's plug in -1. So f of g of -1 equals, again, just take -1 and plug it in for x. Okay. So now let's go ahead and again use our order of operations to see what our output is. So once again, these are two machines working together. They get the same output, but one is giving its own information to the other one. So 2 times -1 gives us -2. Then we multiply by 5. That gives us negative 10. Negative 10 minus another 2 is negative 12. So f of g of negative 1 equals negative 12. Does that make sense? What questions do we have? Okay, now here's a question for us. I put g into f. Will I get the same result if I put f into g? Well, let's find out. So instead of taking this one and putting it in here, let's take this one and put it in here. So this will be g composed of f of x. Okay, so again, we're going to take this one and put it into here. So that means we have 2x. Well, x is the thing we're plugging in for, so this 5x minus 2 goes in here. Does that make sense? Yeah? Okay, good, good. All right, so let's plug in the same thing, negative 1. So we have g composed of f of negative 1. And we want to see if this comes out to be the same thing that we got up here, negative 12. So 2 times 5 times negative 1 minus 2. Okay, again, order of operations. We're going to go into our parentheses first, and we can multiply. 5 times negative 1 is negative 5. Negative 5 minus another 2, that's negative 7. And then negative 7 times 2 is negative 14. So no, we do not get the same thing. And that's important to keep in mind. When we compose functions like this, when we put functions together, the order that we put them in matters. And as to the way in which we put them into an order, just depends on what we want to do in the real world. Okay? Any questions? All right. So again, we can take functions and we can compose them of each other. We can basically take these little machines, put them together to make a more complex machine. Now I want to show y'all something that is a little bit interesting that can happen when we compose these functions of each other, when we plug these functions into each other. So give me a moment to come up with the example here. Because it does matter how I do this. Let's see. Yeah, there we go. Okay, so let me give us two functions. F of x equals, let's say, 2x minus 4. And g of x equals x plus 4 over 2. Now, a keen eye would probably be able to look at this and notice that I have used very similar numbers in both of these. But what really matters in this example is how they're put together. Here we have 2 times x, and then we subtract 4. Here we have x, we add 4, and then divide by 2. So let's see what happens when we compose these functions. So I'm going to start off with f composed of g, and there's a shortcut way of writing that, like that. This little circle here means composed of. It's the exact same thing we did back here, like this, just shortcut. So you might see this somewhere. I'm just showing you so you know what it looks like. Okay, so we have f, which is 2x minus 4. And we're going to plug g in here for x. Right? Any questions so far? Still making sense? Good. So let's go ahead and see what happens here, because we can actually simplify this one. Let's see what happens when we simplify it, though. Let's see, we have 2 times x plus 4 over 2. Well, I'm multiplying this by 2, but I'm also dividing by 2. So what's going to happen with these? I'm dividing by 2 here, but multiplying by 2 here. What's going to happen? Cancels, yeah. Those two things cancel each other out because they're opposites. They're inverse. Okay, so now what we have is, let's see, x plus 4 minus 4. Well, what do we have now? What can we do? We've got plus 4 and minus 4. What are they going to do to each other? Yeah, they're going to cancel as well. So we have f composed of g of x equals x. So if we simplify the thing that we just got, simplify the new function that we got, it just comes out to be x. That's actually a very interesting case. If we were to do the same thing with this, we can't really simplify that much, you know, but it's not going to come out to be x, for sure. Well, in our previous example, we saw that the order matters, right? So what if we go the other way around and put f into g? Will we get something different? Okay, so g composed of f of x. Again, what we're going to do is we're going to take f and plug it in here into g. So that's, let's see, x plus 4 all over 2. And the thing we're plugging in is this, 2x minus 4. So let's see what we get. Well, we don't really need these parentheses, do we? There's nothing multiplying by the parentheses. There's no powers on the parentheses. We can get rid of those parentheses real quick. Okay, so that would be 2x minus 4 plus 4 over 2. Ooh, what's going to happen again? What are those 4s going to do? Cancel. So then we have g composed of f of x equals 2x over 2. Well, again, what happens? Yeah, the 2's cancel, and we get g composed of f of x equals x again. Very interesting. So what's going on here? Why are these so special? These are what we call inverse functions. So again, when I first showed you these two functions, I said this one multiplies x by 2 and then subtracts 4. This one adds 4 to x and then divides by 2. These two functions do exactly the opposite thing of each other. So like here, I'm multiplying by 2, here I'm dividing by 2, here I'm subtracting 4, here I'm adding 4. Not only are they doing the opposite things, they're doing them in the opposite order. So they are exactly opposite of each other. That's why we call them inverse functions. In fact, in this case, another way to write g of x, since we know it's an inverse of f of x, is to call it f to the negative 1 of x. In other words, inverse f. Does this make sense? What questions do we have? None? Okay. So once again, sometimes we have functions that do exactly the opposite of each other. And these are called inverse functions. They're inverses of each other. Inverse functions actually end up being quite useful. So if we remember, on Monday we had that equation that kind of came out to be that weird thing. Let's see. Let's say y equals x minus 2 over 3x. Okay? So this would come out to be one of those weird things. First of all, thinking about this as a rational expression, what can I not plug in for x? What would make the bottom part 0 if I plugged it in for x? Any ideas? What would I have to multiply 3 by to get 0? 0. So yeah, x cannot be equal to 0. Okay, so this is not a linear equation. In fact, this is one of those things that's going to come out to be like this. X can't be 0. Okay, it's going to be something like that. So here we can see, yeah, it does not cross where x is 0. It does not cross that axis. Right here is where x is 0. It cannot reach that point. It can be all these other numbers, but it can't reach this point. However, there's another thing that it can't be equal to, and we can see it in this graph. It can't be equal to x, but it also can't be equal to y. Well, how do we get that? It's by finding its inverse function. If we find the inverse of this equation right here, it will also give us the restriction for y. So the things that x can't be, that's called a domain. The things that y can be is called a range. Now let's see how we get that. Again, in order for us to find our range, we need to find the inverse function. Okay. So the way we get this is we have to do the opposite of what this function is doing right now. Just like we talked about before. These two do the opposites of each other. Well, we got to figure out what the opposite of this one is to find its inverse function. First thing to do, if we want to find that, is to flip x and y. If we change the position of x and y, it's going to make this entire thing backwards. In other words, inverse. So x equals y minus 2 all over 3y. Now what we need to do is solve for y. Okay. So I don't like this fraction. Let's get rid of it. So we're going to multiply this side by 3y so that these cancel. And of course, we have to do the same thing to this side. So now we have, let's see, what's 3y times x? 3y times x is 3 what? yx or xy, either way you want to put it. I'll put it yx, since that's what you said. Okay, and this is equal to y minus 2. Okay, well we want to get y by itself, right? So let's make sure all the y's are on the same side. So I will subtract y from both sides. That gives me 3yx minus y equals negative 2. Okay, anybody got an idea of what I can do now? Again, I want to get y by itself. Think about this side by itself. What could I do to simplify this? What could I do to break it up? By what? You're close. We don't want to divide by x, because that'll just keep the y's on this side would have multiple y's. We want to get all the y's together. We want to divide by y. We want to factor the y out, in fact. So factor the y out, we get y times 3x minus 1. Now all we need to do is to divide both sides by this thing, 3x minus 1. Okay. And then we get y equals negative 2 over 3x minus 1. This is the inverse function. Okay, so what we can say is that if this is the original function, we'll call it f of x. Then this one would be the inverse function. It's f to the negative 1 of x. Okay, so again, what our goal was to find the range of this one, the things that y can be. Well, it's actually the domain of our inverse. So what can I not plug in for x here? Let's see, 3x minus 1 cannot be equal to 0. So I would need to add 1 to both sides. That gives me 3x cannot be equal to 1. And then divide by 3 on both sides. That gives me x cannot be equal to 1/3. So this is the range of our original equation. And that's just one of the places that inverse functions can be useful. I know that was a lot that we just went through, so let me go back over it real quick. We have an equation here. We know that the domain is that x cannot be equal to 0. It can be anything else, but we can't plug in 0 for x. Okay? Now, we also know that there's a range. Every equation has a domain and a range. The domain tells us the things that x can be. The range tells us things that y can be. How do we find that range? Well, we have to find the inverse function, and then the domain, the things that x can't be for the inverse function, will be the range for our original. So, to find our inverse function, we flip x's and y's. We flip their position. And then we solve. So we want to get y by itself again. We go through our solution and get our inverse function. So there's our inverse function. Now we need to find the domain of this and that will be the range of this. So find the domain, x cannot be equal to 1/3, it is the range of this. What questions do we have? No, that made perfect sense. Well, I'm glad, because that was a lot to go over. Okay. So, again, we're used to seeing equations. But equations we can easily make into functions just by making y f of x. And now this is a little machine that we can plug things in for x and it will give us something out for y. Again, it takes an input, processes it, and gives an output. These machines can fit together. Doesn't really matter what two functions you have, you can fit them together. And you do that through a composition of functions. So if I have this one right here, 5x minus 2, and I want to put it together with g of x, which is just 2x, I take this and plug it in for the x of this one. And I can do all sorts of things with it afterward. Now the order in which you do these matters because their outputs will not be the same all the time. However, there is one place that they will always be the same, and that is with inverse functions. So inverse functions, because they are direct opposites of each other, they do exactly the opposite of its inverse. If we compose them of each other, those opposite operations cancel until we just have x. And inverse functions are useful because they help us learn more about our original function. In particular, with this example, what was the range of our original function? Okay, so that is our crash course in functions. Friday, we're going to be taking a little bit more detailed look at these things. Okay? Any questions? All right, then I think that will do it for today. We'll go a little bit early. But again, Friday, we're going to be doing more stuff with functions, just a little bit more detail. So I hope y'all have a good day, and I'll see you then.